Hello students, in our last video we learned about the components of electric circuit and the symbols used when they are represented in diagrams. Today we will learn about Ohm's law. We have already studied the requirements of a circuit to conduct electricity. We have also learned that whenever a potential difference, that is voltage, is applied across a conductor, current passes through it. But is there any relationship between voltage and current? Let us see it. For this, we make a circuit with a battery of 1.5 volts, an ammeter to measure the current, a voltmeter to measure potential difference, a bulb, a switch and a conducting wire, say nichrome wire. Recall students, nichrome is an alloy which is used to make heating elements in toaster, heater, etc. Now let's start our activity. When we switch on the circuit, the bulb glows and the ammeter shows a reading of 0.15 amperes. We note down this reading in the observation table. Now we replace this 1.5 volt battery with a 3 volt battery. When we switch on the circuit again, the bulb glows brighter and the ammeter shows the reading of 0.3 ampere. We note down this reading in observation table 2. We repeat this process by replacing the 3 volt battery with battery of 5 volts and 8 volts one by one. We observe that the current readings in the ammeter are 0.5 and 0.8 amperes respectively. Now let's calculate the ratio of voltage to current. In all the cases, ratio of voltage to current comes out to be 10. Do we see any kind of relationship between voltage and current? Yes. We observe that both voltage and current are proportional to each other. This is very clear from our experiment that every time we increase or decrease voltage, current will increase or decrease in the same proportion, keeping ratio of V upon I same every time. This was observed by a physicist George Simon Ohm. He formulated these observations in the form of the relationship between voltage, current and resistance. According to him, the current flowing through a conductor is directly proportional to the applied voltage across its ends. This is also very clear from our observation table. So we can say that voltage is directly proportional to current. So we can say that V is directly proportional to I. Students, to remove the proportionality sign and convert this to an equation, a proportionality constant is added. So we can write that V is equal to constant into I. Here we take R as constant. Therefore, we get an equation V is equal to R into I. Or we can also write this as V is equal to I into R, where I is the current in amperes, V is the applied voltage or potential difference in the volts, and R is resistance. Let us take the analogy of water flowing through a pipe to understand how the three variables, namely voltage, current and resistance, are interrelated. When we increase the pressure difference across the ends of the pipe, the flow rate of water increases, and when we decrease the pressure difference across the ends of the pipe, the water flow rate decreases. Thus, greater difference implies a greater flow rate. This is similar to the electrical potential difference or voltage across the ends of the conductor. When we increase the voltage, the current increases, and if the voltage decreases, the current decreases. But if the pressure is not altered and kept same, can we regulate the water flow? Yes, we can. Look at these two vessels. If the pressure difference between them is fixed, then the flow of water can be regulated with the valve, that is tap. When we open the valve, the flow of water increases, and when we tighten the valve, the flow of water gets decreased. Here, opening of the valve reduces the resistance in water flow, and tightening the valve increases the resistance in water flow. Similarly, when we increase the resistance in the circuit, keeping the voltage same, the flow of current decreases. And if we decrease the resistance in the circuit, keeping the voltage same, the flow of current increases. In the example of water, we observed that the flow rate of water increases with an increase in applied pressure in the pipe when resistance remains same. That is, the flow rate of water is directly proportional to the applied pressure. While in the example of electric circuit, we observe that the flow of current increases with the increase in voltage. This implies that the current is directly proportional to the voltage, that is, I is directly proportional to V. We also observe in our example of water, the flow rate of water decreases with an increase in the resistance in the pipe, using the valve keeping the pressure constant. That is, the flow rate of water is inversely proportional to the resistance offered by the pipe. In our example of electric current, we observe that the flow of current decreases with an increase in resistance. That is, I is inversely proportional to R. This relationship between voltage, current and resistance is easy to remember using Ohm's law triangle. V is equal to I into R, I is equal to V upon R is equal to V upon I. From this triangle, we can calculate any unknown quantity by hiding it and using the other two. We multiply the two quantities if they are in line and divide the two if one is over the other. For example, if we have to calculate I, then we hide I and divide V by R as they are one over the other. Now students, we know that R is a proportionality constant for the given metallic wire at a given temperature and is called its resistance. We can say that resistance is the property of a conductor to resist the flow of charges through it, since it is inversely proportional to current. Its SI unit is ohm and we represent it by the Greek letter omega. According to Ohm's law, we say that R is equal to V upon I. And suppose if the potential difference across two ends of a conductor is 1 volt and the current flowing through it is 1 ampere, then the resistance R of a conductor will be 1 ohm. That is, 1 ohm is equal to 1 volt upon 1 ampere. Now, if we plot the graph between voltage and current, then we get a straight line that passes through the origin of the graph. This implies that V upon I is a constant ratio. Students, do you know all conductors do not obey Ohm's law? The conductors which obey Ohm's law are called ohmic conductors, while the conductors which do not obey Ohm's law are called non-ohmic conductors. Semiconductors like germanium and silicon do not obey Ohm's law. So students, in this video, we learned that the current flowing through a conductor is directly proportional to the applied voltage across its ends. This is called Ohm's law. This is also very clear from the graph of Ohm's law, which is straight line. The conductors which obey Ohm's law are called ohmic conductors, while the conductors which do not obey Ohm's law are called non-ohmic conductors. In the next video, we will learn more about resistance and various factors affecting the resistance.